All right, guys, back here together to talk some more about ionic compounds and naming ionic compounds. Being able to write the name and write the formula, go both ways with it. This time we're talking about the special cases of when there's transition metals. Sometimes we refer to them as special metals, and they're special just simply because they have multiple oxidation numbers. Okay, so what do we do in the case where we're dealing with a metal in an ionic compound that is a transition metal or special metal? We're going to use the stock system, which simply means that we're going to use Roman numerals to tell us the charge of the metal, since the metal can have multiple oxidation numbers. Okay, we use this when metals can have multiple oxidation numbers. So a lot of metals can have multiple oxidation numbers. Most of those would be your transition metals, or I shouldn't say most. All of them are either your transition metals or your P block metals, right? All of group 1 is +1s, all of group 2 is +2s, and then aluminum's a 3, zinc is a 2, and silver is a 1. So we don't have to use the stock system. We don't have to use the Roman numeral thing when it comes to those metals because they always have the same charge. But the other ones, we're going to use the stock system because they can have different charges. Okay. Now, technically, there's some other elements that are in the transition metal category that has one oxidation number. But rather than you having to memorize all the ones that just have one oxidation and know what it is, I felt like it'd be easier that we would just use the stock system for anything that wasn't a group 1, group 2, or these simple 3 here. Those 3 are pretty easy to remember because they make a nice little kind of diagonal right here. A +3, a +2, and a +1. So I figured that y'all could kind of have that down pretty easy. And then be able to go from there with the rest of them. Okay? So about those multiple oxidation numbers, a couple things I wanted to point out to you. I've given you this chart. This chart doesn't have every single element on it, but it has the most common metals and what their charges are. Okay, so there's some that's not here. Yes, I know. Okay, but these are the ones that you would probably be coming across with stuff that I would give you, or some, even outside of this class, the most common metals that are going to be used. Okay. I also uploaded a picture of this periodic table, the one I just showed you a second ago. I know this is like super not legible for you here, but hopefully the picture that I uploaded for you, you can actually take this. It's just of the periodic table that we have over there, and hopefully on the picture you can kind of zoom in and you can see what the oxidation numbers are, because on this particular periodic table, in the upper right hand corner of each of the elements, it lists the oxidation numbers for that particular element. Okay, so hopefully you can use that. If not, then you can just Google search and you can find the oxidation number. Just search for periodic tables with oxidation numbers. Hopefully you can find one that'll work for you. Okay, but honestly, as far as the metals go, this chart should serve your purpose. In addition to that, when it comes to the non-metals, noble gases, group 18, they don't have any oxidation. They're not bonded with anything. Group 17, they're all -1s. Group 16s, they're all -2s. Group Group 15, they're all -3s as far as all the non-metals are. And then group 14, you've got carbon, it's a -4. Okay, so let's get into doing this a little bit. When it comes to giving the name and writing the formula, this is just as easy as what we just did with the ionic compounds without transition metals. In fact, it's probably a little bit easier because in the name we actually tell you the charge of the metal, so you don't have to go look it up on the periodic table or look it up in the chart. It tells you what it is, right? So we would read this as nickel 3 oxide. Nickel 3 oxide. Okay. So the Roman number 3 tells me the oxidation number of the nickel is +3 in this case. Okay. And then oxygen, I know based on the periodic table that the oxidation number of oxygen is a -2. So we got Ni +3 and then O -2 with their charges, right? So what we learned previously is the same thing. Is the next thing we do is we do our little swap and drop, right? So when we swap and drop, we end up with 2 nickels and 3 oxygen. Ni2O3 would be that formula for this nickel 3 oxide. Okay. Once again, we have to use this because nickel can have more than one oxidation. Nickel can be a +2, it can be a +3, it can even be a +4 upon occasion. Okay. So this particular nickel is a nickel 3, meaning its charge is 3. Doesn't mean that it has 3 down here. Don't get confused there. The subscript's not 3. We're not using 3 nickels. It has a charge of 3. When we do the swap and drop, it actually tells us I got 2 nickels and 3 oxygens. All right. That's super simple. Going the other direction, if we're given the formula and we're writing the name, we have to do a little bit of math to figure out what the oxidation of the metal is, so then when I write the name, I can write the correct Roman numeral, right? So I got a few slides here to help us practice finding the oxidation of the metal, okay? And real simple, what we do is we take the oxidation of the nonmetal and we use that and kind of work backwards from there to find the oxidation of the metal. Because we're dealing with a neutral compound, so whatever the charge of the negative side is, the charge of the positive side has to be the same. Well, equal but opposite. Negative side is going to be -8, the positive side would then have to be +8, or so on. Okay? So looking at this example here of this lead chloride, PbCl2. Okay? I'll write it on the board here as well. PbCl2. Alright? The first thing we're going to do is we're always going to start with the nonmetal, because the nonmetal is an oxidation that I can know. It's not changing. Chlorine's always a -1. Okay? So over here on the board, I'll actually write kind of what you would write on your paper as you do this. So the best thing you can do is just kind of draw a line where you're dividing the compound in half to its cation positive side and its anion negative side. And we just simply say, okay, charge of the chlorine times how many chlorines we have, and that gives us the charge of this whole side would be -2. Charge of this whole side is -2, right? So if the negative side is -2, then the positive side would have to be +2, right? If we go back to what we were talking about here, just taking a separate problem here, but if I've got potassium and oxygen, then since this is -2, then I'm going to need a +2, the potassiums, in order to balance that out, right? So one potassium wouldn't do it. I would actually need 2 potassiums, right? So what we're doing is we're working with problems where we don't actually know the charge of the metal, so we don't know how many of them to put there, okay? Or we don't know how to write the name and go in the opposite direction, okay? So if the chlorine side is -2, then that means the lead side would have to be +2, right? And then what we simply do is we divide by how many of these guys we have. In this case, we only have 1 lead, so if you divide by 1, you just end up with the same number. You end up with a +2. So in this case, each lead is a +2, has a +2 charge, has a +2 oxidation, okay? Oxidation of chlorine is -1. We simply multiply by how many chlorines we have to give us the charge of that whole side, -2. Compounds are neutral, so the positive side's got to equal or balance out the negative side, so it's got to be a +2. There's only 1 Pb, so that means that that whole side is the charge of that 1 Pb is indeed +2. All right, looking at another example here. This time we'll look at a bismuth oxide. What we're doing here is once we find the charge of the metal, then we could write the name of the metal. Then we would know what Roman numeral to put there when we write the name of the metal, right? So we're practicing this, and then we'll actually do some problems where we write the whole name, okay? So find the oxidation number of the metal, once again, of the bismuth, the Bi. We're going to start with what we know. Oxygen has a -2 charge, right? There are 3 of them. That comes from right there. I don't know if you can see colors. I'll put this in a different color to help out. Okay? Which means that this whole side is a -6, right? So since there's 3 oxygens, each of the oxygens are -2, that gives me a total of -6, right? So each oxygen's -2. If I have 3 of them, get my fingers in here. then I would have a -6 altogether. 1, 2, 3, 4, 5, 6, right? That kind of thing. All right, so that means that on the positive side, I need a +6. So this guy tells me that this is a +6. Now this is the charge not of each business, but the whole positive sides, right? So then I take and I divide by how many business that we have, right? So we have 2 of them. 6 divided by 2 gives me +3. So this is the oxidation number of the business. So business would actually have a +3 oxidation, okay? Now, I'm going to break some rules here, and I'm going to tell you real quick something that you can do sometimes. It doesn't always work. I'll tell you when it works and when it doesn't work, okay? Sometimes that all we really have to do, if I erase this here, well, I'll just write over here to the side. Sometimes if I would, because we know when we wrote this formula, what did we do? We did the swap and drop, right? So if we reverse the swap and drop and kind of go backwards here like this, right? So we got business, we got oxygen. If we reverse the swap and drop, then that would tell me this would have to be a +3 because the first one's always positive. And then the oxygen would be a minus, here's the 2, coming back up here would be a -2. So just by reversing the swap and drop, I see that the business is a +3 in this case, okay? That works as long as it's not a problem where we have simplified or reduced, right? So when we did the swap and drop here, 2 and 3 were not divisible by the same number, so I didn't have to reduce or simplify the problem, right? If we were doing a problem where simplification did occur, like say, zinc oxide. If we take zinc oxide, and it's understood that there's a 1 here and a 1 here. We don't have to write it, right? That's understood. If I reverse the swap and drop and come here and come here, then I would be saying +1 and then -1, right? This one took us here. This one comes back up here. Of course, the first one's a positive. The second one is a negative. All right? But that's not true, okay? Zinc's actually not a +1. Oxygen's not a -1, okay? So this didn't work for me, and the reason this didn't work for me is because when we wrote this problem, we actually reduced the problem, okay? So, remind you, if I start back out, zinc, oxygen's actually a -2, zinc's a +2. So when I write the formula, and I swap and drop, I end up with a 2 and a 2, right? So because both of these are divisible by 2, when we divided both of them by 2, we simplified it and end up with just this ZnO, zinc oxide, right? So it doesn't work, the whole reversing the swap and drop thing doesn't work if the problem has been simplified. But if it hasn't been simplified, that will work, okay? So how do you know if it's working or it's not working? If when you reverse the swap and drop, if you look at your nonmetal, and it has the correct oxidation number, then it worked. If when you reverse it, you look and your nonmetal has the wrong oxidation number, it didn't work, and you got to do the math, okay? In that case, you're going to have to do the math. You can't just reverse it. Does that make sense? Hopefully. All right? If the super secret doesn't help or it doesn't make sense to you, then just kind of stick with what the slide says. Stick with the information there. Okay, so when it comes to actually writing the name, it's real simple. Steps 1 and 3 is what we already know as far as naming ionic compounds. We name the metal, and then we're going to name the non-metal with I. The only thing we're doing is we're sandwiching in between there, where we're going to write the charge of the metal as a Roman numeral in between the two names. Okay, so first we have to find the charge of that metal by doing the math that we just did here. So if we look at this particular problem, we have a copper oxide. Now copper can be a +1, so this could be a copper 1 oxide, or copper can be a +2, so this could be a copper 2 oxide. So when I'm writing my name, I got to know what Roman numeral to put down here when I say copper oxide. Which copper oxide, all right? So we start with the nonmetal. We know that oxygen is a -2. There's 1 of them, so that gives me a charge of -2 for all the oxygens. So the copper, the charge of all the coppers would then be a +2, there's 2 coppers, right? So 2 divided by 2 gives me a +1. So each of the coppers is a +1. So since copper has a +1 charge, a +1 oxidation, we would say this is a copper 1 oxide. Roman numerals for the charge of the copper 1 oxide. Okay? One more here. This is a tin nitride. Okay? Tin nitride. So we want to know which tin is it. Tin can be a +2 or tin can be a +4. So we start with the nitrogen. What's the charge of nitrogen? It's a -3 based on where it is on the periodic table. Times 4 of them gives me a total charge of all the nitrogens to be -12. So then the positive side, the metal side, the tins have to be a +12, right? Divided by how many tins we have? We have 3 tins. So 12 divided by 3 gives me 4 for each of the 10 atoms or 10 ions, right? So we have a charge of 4, an oxidation number of 4 for the tin. So we would say this is 10,4 nitride. Oops. 10,4, if I get that thing to go away, you'll be able to see it again. 10,4 nitride, okay? Parentheses there for the Roman numerals. All right? So that real quick is ionic compounds with transition metals going both ways, writing the formula and writing the name given the formula. Okay? Let me know if you have any questions.